Hi students, in this module we are going to discuss about the determination of focal length of a given biconvex lens by using UV method. In the earlier classes we already did how to find the focal length of a convex lens and how to identify the images and how to study the properties of the images, that what we already learned. In this module we are going to learn the focal length of the lens by using UV method. Already studied method only this is. For example purpose, you see the experimental setup. Already what we did in that activity is we placed the lens stand or otherwise V stand on the lens table at the center of the lens table on the principal axis. Now on one side of the lens we kept the object. The object is nothing but glowing candle. Then on the other side we kept the screen. Now in the very beginning, first of all we should place the candle at very far distance, approximately 120 centimeters distance we should place. Now we are taking the distance between lens stand and the object. The distance is called object distance. We should place the screen on the back side of the V stand or otherwise lens stand, and then we should move the screen slowly away from the lens. At a particular distance we can get a small dotted image of the candle. Now by measuring the distance between the lens stand and screen we can calculate the image distance. For example, if the serial number 1 image object distance u is for example say 120 centimeters and image distance some value will be there, x values. By substituting this 120 centimeters and as well as x centimeters in 1 by f is equal to 1 by v minus 1 by u, we can get the focal length of the biconvex lens when an object is at a distance of 120 centimeters. In the second case, means in the serial number 2, we should place the object at a distance of 100 centimeters. Now the object distance is 100 centimeters. Again we should place the screen very nearer to the lens stand. Move the screen slowly away from the lens stand. At a particular distance we can get the image. That distance is called image distance. Again note down that value as y readings. Now by substituting the 100 centimeters and as well as y centimeters reading in the formula 1 by f is equal to 1 by v minus 1 by u, we can calculate the focal length of the given lens. Like that only we should perform the activity even for 80 centimeters, 60 centimeters, 40 centimeters, 20 centimeters of the image distance. And every time we should note down the value of image distance. For every time we should substitute the value of object distance and image distance in the formula 1 by f is equal to 1 by v minus 1 by u. Then finally we can get the value of the focal length f is equal to uv by u minus v. So from this activity we can find the focal length of a given biconvex lens by using UV method. UV method is nothing but U stands for object distance, V stands for image distance. By substituting the values of 1 by f is equal to 1 by v minus 1 by u. From this we can calculate the focal length of a given biconvex lens by using UV method. Here what are the precautions to be taken? While conducting this activity it should be dark. Why? Because if other side onwards the light is coming, means external light is coming, we can't see the image in a proper manner. Second precaution is measure the distance, that is object distance and image distance accurately. Third one, apply the sign conventions while substituting the formula 1 by f is equal to 1 by v minus 1 by u. This is the experimental procedure and as well as experimental setup while using biconvex lens and by knowing the focal length of a biconvex lens. Till now, we determine the focal length of a biconvex lens by using UV method. Find out the focal length of the convex lens depends on some of the factors. Let us come to know what are the factors that they determine. It depends on the nature of the material that is used. That is, by what material the lens is made up of. Sometimes the lens is made up of either ruby or sapphire or crown glass or flint glass or some other material. As the material changes, the focal length also changes. As the object distance changes, focal length is always constant. Means focal length of a given lens is always constant. It does not depend on some factors. Some of the factors it depends on, that is refractive index. We already know it is represented by letter N. This refractive index is depending upon the nature of the material of the lens. And one more factor, that is nature of the surrounding medium. As the surrounding medium changes and the refractive index changes, automatically focal length also changes. So these three are the factors that affect the focal length of a given convex lens. As we already know, the focal length of a lens depends on the nature of the surrounding medium and as well as refractive index of the surrounding medium. Here let us discuss one example. What is the example here? They provided a lens for us. That lens is made up of quartz glass. Refractive index of that quartz glass is 1.4. And they given different kinds of the material medium. Air whose refractive index is 1.0, water whose refractive index is 1.33, benzene whose refractive index is 1.50. Here, if the lens is immersed in water, in this case, lens is immersed in water whose refractive index of water is 1.33. Refractive index, now this is water and here it is lens which is made up of quartz glass whose refractive index is 1.4. Refractive index of water is 1.33. Observe here, refractive index of the given lens is greater than the refractive index of water. That means refractive index of quartz glass is greater than the refractive index of water. Now this lens acts as a converging lens. Why? Because refractive index of the surrounding medium is less than the refractive index of the lens. Then the lens acts as a converging lens. If you consider, this is the same lens which is made up of quartz glass whose refractive index is 1.4. It is immersed in a medium, that medium is benzene. The formula for benzene is C6H6. Now it is immersed in benzene whose refractive index is 1.5. Now see here, refractive index of the quartz glass is less than the refractive index of benzene. This means refractive index of the surrounding medium is greater than the refractive index of the quartz glass or otherwise lens. Now this lens behaves as a diverging lens. Like that, we can observe the air bubble which is formed on the soap solution. Even the soap solution also behaves as a diverging lens, that is depending upon the refractive index of the surrounding medium. From this explanation, what we can find out? The behavior of a lens depends on the refractive index of the surrounding medium. If the refractive index of the surrounding medium is less than the refractive index of the lens, then the lens behaves as a converging lens. If the refractive index of the surrounding medium is greater than the refractive index of the lens, then the lens behaves as a diverging lens. Same lens only, but behaving in different manner, that is converging and diverging, that is depends on the nature of the surrounding medium and as well as refractive index of the surrounding medium. Now we are going to learn one more activity, that is the focal length of a given lens, what we already calculated, changes whenever it is immersed in water. Why? Because as I already said, focal length of the lens depends on the nature of the material medium, surrounding medium and refractive index of the surrounding medium also. Now see this activity here. There is a glass beaker is there, large glass beaker is there. At the bottom of the large glass beaker, we should place a black stone. Whenever the black stone is there under water, we can see it in a very clear manner. So for that we are taking a black stone. Then pour the water up to the edge, up to the brim of the large glass beaker. Then we already know focal length of a given lens. Insert the lens to the circular lens holder. Then insert that circular lens holder into the water. By immersing the lens into the water and by adjusting the distance between the lens and holder, we can observe clear image of the stone. For example, if we consider this is the stone and this is the lens, here is the image that is formed. This means size of the object is equal to size of the image. That is, this is nothing but radius of curvature of the lens in water. This also becomes the radius of curvature of the lens in water. Now we calculated the radius of curvature of the lens in water. If we made it half, that is r by 2, we can calculate the focal length of the lens in water. We calculated the focal length of the lens in water. We already know focal length of the lens in air. Now by comparing the focal length of the lens in air and focal length of the lens in water, it is proved that focal length of the lens in water is 2 times than the focal length of the lens in air. That means as the surrounding medium is changed, focal length of the lens also changes. That means whenever a lens with known focal length is inserted in water, its focal length becomes double. What we did in this activity roughly, we inserted the lens into the water, we calculated the radius of curvature of the lens by using the scale. So total what are the apparatus that is required? A glass beaker is required, a black stone is required, water is required, lens with known focal length is required and a circular lens holder is required. We calculated the radius of curvature of the lens in water by making it half we calculated the focal length of the lens in water, and by comparing the focal length of the lens in water with respect to the focal length of the lens in air, it is proved that focal length of the lens in water is twice that of the focal length of the lens in air. From this activity, we already proved that focal length of a given lens is increased when it is immersed in water. Generally, it becomes twice when it is immersed in water.